Hello, everyone. I am Dr. Eris, and I am thrilled to welcome you to our session today. We are about to embark on an extraordinary journey to the very edge of reality, the subatomic world. To navigate this tiny landscape, we use what's known as the Standard Model. Think of it as the periodic table for particle physics. Just as the familiar periodic table organizes chemical elements, the Standard Model provides the definitive map for nature's most fundamental units. Our quest in this class is to define and understand the smallest building blocks of the universe, the point where we can no longer break things down any further. As you can see in our hierarchy chart, we categorize these particles into two main families. First, we have the fermions. These are the matter builders, the particles that give the universe its physical structure. Then we have the bosons, the force carriers. If fermions are the bricks of the universe, bosons are the invisible hands and the mortar that dictate how those bricks interact and stick together. Let's move forward and take a closer look at the matter builders themselves. Building on the bricks and mortar analogy we just covered, let's focus on the bricks, the fermions. These are the fundamental particles that build the substance of everything we see in the universe. Fermions are defined by a quantum property called spin. Specifically, they have a spin of 1/2. This intrinsic angular momentum means they follow the Pauli exclusion principle, which effectively prevents matter from collapsing into itself, giving the world its solid structure. The most famous fermions are quarks. As you can see in this properties table, they come in 6 flavors, organized into 3 generations. Notice the electric charges. Unlike most things in nature, quarks carry fractional charges like +2/3 or -1/3. Quarks are social particles. They are never found alone. They combine to form hadrons. Take a look at these formulas. A proton is made of 2 up quarks and 1 down, totaling a charge of +1. A neutron, on the other hand, uses 1 up and 2 downs to reach a neutral charge of 0. This simple subatomic arithmetic is what makes the building blocks of every atom possible. Building on what we just covered regarding quarks, let's turn our attention to the second group of fermions, the leptons. Unlike quarks, these particles do not participate in the strong nuclear force, which gives them a very different role in the structure of our universe. In generation 1, we find the most familiar lepton, the electron. Along with its partner, the electron neutrino, it is responsible for forming stable atoms. Without the electron's negative charge, the chemistry that makes up our world simply wouldn't exist. As we move to generation 2, we encounter the muon. Think of it as a much heavier version of the electron. It isn't stable enough to form ordinary matter, but we can detect it frequently in cosmic rays that strike our atmosphere from space. Finally, generation 3 introduces the tau. This is the most massive lepton of all, so heavy and unstable that it exists only for a fraction of a second before decaying. Each of these 3 generations is paired with a corresponding ghostly partner called a neutrino. Neutrinos are particularly mysterious. They are nearly massless and have no electric charge, meaning they pass through almost everything, including you, without leaving a trace. It's one of the great mysteries of physics why we have exactly 3 generations of these particle pairs. Maya, I see you looking curious about this pattern. Do you have any thoughts on why nature might repeat itself this way? Building on the fermions we just covered, we now turn to the mortar that holds the universe together, the gauge bosons. These particles are responsible for all the fundamental interactions we observe. A key concept to grasp is that forces aren't just invisible pulls. They occur through a messenger exchange. Imagine 2 people on ice skates throwing a heavy ball back and forth. That ball is the boson, and the act of throwing it pushes them apart. Let's watch this short visualization to see how this exchange process actually works at the subatomic level between interacting particles.
粒子通过交换一个能量量子，也就是我们所说的玻色子，来传递相互作用。
As you can see, different forces have different messengers. Photons carry the electromagnetic force, while gluons act as the sticky force holding atomic nuclei together. The W and Z bosons manage the weak force, which is what allows radioactive decay to happen. Finally, look at this comparison of relative force strengths. You'll notice the staggering difference between them. The strong force is vastly more powerful than the others, which is why it takes so much energy to break an atomic nucleus. Next, we'll move on to the particle that gives these messengers their mass. Building on what we just covered regarding the force carriers, we now arrive at the missing piece of the puzzle, the Higgs boson. It's often called the God particle, but in physics, it's the key to understanding why matter has substance. To understand the particle, we first have to understand the Higgs field. Imagine a universal energy field that permeates every inch of the cosmos. It's not like a magnetic field that only affects certain metals, it is everywhere all the time. This formula represents the field's potential. Because of this specific mathematical structure, the Higgs field remains on even in a vacuum, creating a background against which all other particles must move. Now, mass is not an inherent property, it's the result of interaction. Particles acquire mass by dragging through this field. Think of it like walking through water. The more you interact with the water, the more resistance you feel and the heavier you seem to be. This remained a theory for nearly 50 years until the 2012 discovery at CERN. By smashing protons together at nearly the speed of light, scientists finally caught a glimpse of the Higgs boson, proving the field exists and cementing our understanding of the Standard Model. Welcome to the Particle Physics Lab. Here we can observe how different fundamental particles interact with forces and the Higgs field. Use this selector to choose the particle you want to investigate, such as quarks or electrons. This slider adjusts the strength of the fundamental forces, like the strong or electromagnetic force, affecting particle motion. Notice that photons have zero interaction with the Higgs field, which is why they are massless and travel at the speed of light. The Higgs interaction slider simulates the drag a particle feels. More interaction results in more mass and slower movement. Quarks interact strongly with each other and have significant mass due to their interaction with the Higgs field. And because of those interactions with the Higgs field we just covered, we have finally reached the ultimate destination of our journey today. This is the full map of the universe, the Standard Model of particle physics. As we've categorized throughout the session, our inventory is now complete with 17 fundamental particles. We have the 12 fermions that build matter, the 4-gauge bosons that carry forces, and the Higgs boson that grants mass. This table is arguably one of the most successful theories in human history. It organizes every particle by its properties, its charge, its spin, and its mass. Take a moment to look at how the quarks, leptons, and bosons are all interconnected in this elegant framework. Notice how the 3 generations of matter are vertically aligned, Leo. This is that perfect structure you were looking for earlier. Everything from the smallest atom to the largest star is accounted for within these blocks. It is a remarkably compact summary of reality. Now that we have the full map in front of us, we are ready to see how well you can apply this knowledge. We'll move shortly to our final assessment to test your understanding of these interactions. Building on our realization that the Standard Model is incomplete, we arrive at the final frontier of our course, what lies beyond it. The most glaring omission is gravity. While general relativity explains the macro world of stars and galaxies, it refuses to play by the quantum rules we've spent this session discussing. This gravity gap remains the biggest hurdle in creating a unified theory of everything. Furthermore, we must account for the dark sector. As shown in these cosmological density parameters, dark matter and dark energy make up about 95% of the universe. This means all the quarks and leptons we've studied represent only a tiny fraction of what's actually out there. Looking ahead, the search for new physics continues with the high-luminosity LHC upgrades and theories like supersymmetry. We are essentially hunting for an unknown piece of the mathematical puzzle, the missing part of the universe's master equation. We've journeyed today from the smallest building blocks of matter to the very edge of human knowledge. It has been an absolute pleasure exploring the subatomic world with all of you. Remember, every gap in our current model is an invitation for the next generation of physicists to make history. Thank you for your incredible focus today.